Welcome to Get Your FRQ On. This is from the Calculus AB exam 2001, question 4. In the question stem, we're provided very little information about a function h of x, but we are given an explicit formula for the first derivative of h. In part A of the question, we are asked to find where the graph of h of x has a horizontal tangent line and whether or not h of x has a maximum or minimum at these points or point. So based on what we know about horizontal tangent lines, we know that horizontal tangent lines will occur when the first derivative of h takes the value 0. We were given an explicit formula for h prime of x, so we'll just need to take that formula, set it equal to 0, and then solve. So h prime of x is x squared minus 2 over x, and we want to know when that will equal 0. Right? That will equal 0 whenever the numerator is 0 and the denominator is not. So we take the numerator, x squared minus 2, set it equal to 0, solve it, and we get x equals plus or minus the square root of 2. It's probably worth noting here that h of x does have a discontinuity at x equals 0. So this may affect portion of our solution later on. In fact, knowing what other questions are being asked in this free response question, we definitely have to take account of the fact that h prime of x has a discontinuity at x equals 0, as does h. To determine whether it's a maximum or minimum at these points, we'll use the second derivative test. We'll check it for concavity, and we'll make our determination about maximum or minimum. To do this, we have to find a formula for h double prime of x. If we use the quotient rule, we can determine that the second derivative of h is x squared plus 2 all over x squared. If I then evaluate the second derivative of h at both negative square root 2 and positive square root 2, each of those turns out to be positive 2, and notice that both, 2, since we get it both times, is greater than 0, and so we can conclude based on this that the graph of h is concave up at x equals negative square root 2 and also at x equals positive square root 2. Thus, because of the second derivative test, we conclude that h of x will have relative minima, at each of those points. They are both relative minima of h of x at x equals negative square root 2 and x equals positive square root 2. In part B, we are asked to determine intervals where h of x is concave up. In order to do this, we have to understand how we determine whether or not h will be concave up. Right? H will be concave up whenever the second derivative of h is positive. Now, we found we were given the first derivative in the question stem, and we found the second derivative in part A in order to determine whether h had maxima or minima at its horizontal tangent line points. So we already have a formula for h double prime of x. We can import that and use it again here. So our formula again for the second derivative of h is x squared plus 2 over x squared. Since the numerator, x squared plus 2, will always be greater than or equal to 2, and the denominator will never be 0, since 0 is not in the domain of h, we conclude that h double prime is positive for all x not equal to 0. So, as long as x is not equal to 0, we see that h of x is concave up everywhere on its domain. If we write this in interval notation, which you may or may not have to do, if you're comfortable with interval notation, I highly recommend using it. But in interval notation, h would be concave up from negative infinity to negative square root 2, negative square root 2 to 0, 0 to positive square root 2, and positive square root 2 to infinity. Notice, because x equals 0 is not in the domain of h, we do have to break off our intervals there. We can't cover negative square root 2 to positive square root 2 in one interval, because then we'd be saying that it's concave up at x equals 0, which is impossible. In part C of the question, we are asked to determine the equation for the tangent line at x equals 4. In order to write the equation of the tangent line to the graph of h at x equals 4, we need to know both f of 4 and f prime of 4. Fortunately, in the question stem, we are given the value of f of 4. We are told that f of 4 is negative 3. It's one of the only things we know about f other than what f prime is. So we have our specific x value, we have our specific f of x value, and since we have a formula for f prime, we can find or evaluate f prime at 4 using the provided formula. If we do that, we find that the derivative of h evaluated at 4 is 7 over 2, or 3.5. We have a slope, we have an x-coordinate, we have a y-coordinate. I would recommend writing the equation of the tangent line in point slope form. So in point slope form, we would get y plus 3 equals 7 halves times x minus 4. You're more than welcome to simplify this and write it in a different form. However, this form is acceptable, and once you have an acceptable answer, might not be a bad idea to just move on and save that time for another question. In part D, we are asked if the tangent line at x equals 4 for h is above or below the graph when x is greater than 4. So in order to answer this, we have to check concavity again, right? If the graph of h is concave up at x equals 4 and remains concave up when x is greater than 4, then the tangent line will fall below the graph of h. If h is concave down at x equals 4 and remains concave down for x greater than 4, the tangent line will be above the curve for x is greater than 4. So we have to check concavity here, but we already found the intervals for which h is concave up, right? We have a second derivative for h. We found that. That's x squared plus 2 all over x squared. If we plug in x equals 4, we get 18 over 16, which is positive. Doesn't really matter what the value is. H double prime is positive for x equals 4. In fact, we determined earlier, unless it's negative square root 2 or positive square root 2 or 0, h is concave up pretty much everywhere. So yes, h has to be concave up at x equals 4. But that also means that h is concave up for all x greater than 4. So if h is concave up for all x greater than 4, then the tangent line at x equals 4 should be beneath the curve. So because the graph of h is concave up for all x greater than 4, we know that the tangent line will lie below the graph of h of x on the interval where x is greater than 4.